Okay, I'm gonna restart. Hello there. My name is Axel. This is my first video. It's a bit weird. So I'm on the grounded low voltage team for my FSAE team at my school, and we were tasked, or I was tasked to simulate the circuit. It's called a TSAL circuit or a TSAL circuit. Um, and I think it stands for Attractive System Awareness Lighting or Awareness Light. And I'll walk you through how the circuit works because I had no idea how it worked. And I guess this is like consolidation for myself. Okay, so I was given this schematic and I was like, oh my goodness, what the flippity dippity do I do? I have no clue what's going on here. So here we go, Falstad. I recreated the circuit and I'm just gonna walk you through it. So on the left here, oh, and later on I'll like explain more in depth on like each component. But I might be wrong in some stuff because I still don't really know what this is entirely. So if I am wrong, just let me know. Okay, so this entire circuit is based off of these two inputs called the BMS and the IMD. The BMS, if I'm not wrong, stands for the Battery Management System, and the IMD is the Insulation Monitor Device, something like that. And I'll run the simulation in a bit, but basically, you're going to have these 5 volts come through. It's going to blah, blah, blah. If this is on, this entire circuit here will all be 5 volts. And if this is on, then these wires will also be 5 volts. And both of these wires connect into a logic gate, which are these things. This is an AND gate. The other one is a NAND gate. So yeah, they're just these things, like these ways that computers can compute stuff. I guess it's like if, for example, we take the AND gate, which is this one. If you have this is on and that is on, then your output will also be on. But if this is off and off, this will also be off. Basically, what I'm saying is for this output to be on, both of these have to be on. You can, here's a photo if you want to look at it. Yeah, 1, 1 will give you a 1. But if you only have 1, 1 and 1, 0, it'll give you a 0 because they both have to be on because it's an AND. A and B have to be on. A NAND gate is like the opposite of an AND gate, so it'll just give you the opposite values. If you have 0, 0, which would give you a 0 in an AND gate, it'll give you a 1 in a NAND gate. So that's that. Yeah, so this is an AND gate, that's an AND gate. The NAND gate will do the opposite of the AND gate. Okay, so now that we have that, the point of the TSAL system is to let members of the FSAE team know if a car is safe to touch or not. And if it is safe to touch, this green LED light will turn on. And if the car is not safe to touch, the red LED light will start blinking at a certain frequency. I think it's like 2 to 5 hertz, but I don't really know. It's in the rule guide somewhere. Okay, so let's turn this on and we'll see what happens. So let's run the simulation. So here we get a voltage from the BMS, we get a voltage from the IMD, and I'll explain what the BMS and IMD is later. And here, so both of these are on. So we have a output at the AND gate. So this is on. And this links into a transistor. I'll also talk about that. But basically, it's drawing 12 volts from this source, and it's telling the LED light to turn on. Great. And if we look at the other side, on will give you off because it's the opposite of the AND gate. And as you can see here, blah, 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 we go through here and the red light is not not flashing. All right, great. So the BMS, so the green light works when the BMS and IMD are working happy. Let's say the BMS falls and it goes to 0. Uh-oh. bad. We got red LED light and starts blinking, and that's kind of what we want. And let's say the IMD also falls to 0. Notice how it still keeps blinking. And I think that's because the red LED light is connected to a separate battery, and it will keep blinking even if both of these are off for like 15 minutes after. So I'm gonna have to reset the simulation to, yeah. Okay, so you might be asking now, well, that's great and all. I roughly know how the TSAL circuit works, but what exactly are these inputs? What is the BMS? What is the IMD? Well, yeah, we know it's the battery management system and the insulation monitoring device, but how do those work? Okay, let me pull up my 3D paint. Okie dokie. So the IMD. So I drew this thing in blue is like a rough sketch of the chassis of the car. And let's say this red thing is like the accumulator or the battery of the car, right? It has these two positive and negative terminals. And uh, let's say you're a driver sitting in the car, or I should use this marker. Let's say you're a driver sitting in the car. And notice how the wires connect through the chassis, right? So let's say you're the driver, you're connected to the chassis, so you're technically connected to the circuit. And let's say you happen to touch this that terminal of the battery. Uh, Basically, what's going to happen to you is you're going to get shocked really badly because you're creating a circuit kind of. So the uh, creating a circuit like this, blah, 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 blah. And current's going to flow through your body and you may die. Maybe, I don't know. The battery is very powerful on these things. So what the IMD does, oh, and because of that, we insulate the terminals on the accumulator so that the driver can't accidentally touch them. And so what the IMD does is it measures the insulating resistance of the chassis. I'll do a different color of the chassis, and it compares it with these terminals. And if it measures that the battery is sufficiently insulated, then everything will be good, and you're going to get a positive voltage. And so if everything is good, this IMD will input a plus 5 volts into this TSAL circuit. And if it's not good, if the IMD detects like that the battery is somehow connected to the, or like, how should I put this? Is like, is connected the right word? I'm not sure. Connected to the chassis, it'll like start shutting down the system of the car because it'll electrocute the driver if he touches one of these poles, and so the whole system will turn off and the IMD will not input a plus 5 volts into our TSAL circuit. All right, so that's the IMD. Let's talk about the BMS. The BMS is a bit simpler. Basically, in the car, you have a bunch of batteries and they form together to make a pack. And what this battery management system does is it like looks over all these mini batteries and lets them work together optimally. The two main things it looks at are the temperature of the batteries and the charge of the batteries. And if something goes wrong, the BMS system will turn off and you'll get 0 volts from this into this TSAL circuit. So those are the two inputs, basically, in a nutshell, really quickly. And okay, I'll run you through this scenario. Let's say both of these are off. So that is off. okay, let's just say one of them's off, and we get this scenario going on. This thing here is called a 555 timer, and it lets the LED flash on and off basically. Because I think in the rule book it said that you can't program the LED to flash on and off using software, so you have to do it using hardware, and I guess this is how they do it. Um, all right, so let's go back to the other situation. Now let's talk about this situation. Both BMS and IMD are on. Good, good. It goes into this AND circuit. This is on. And this is called a transistor here. To my knowledge, there's two main types of transistors, a BJT transistor and a MOSFET transistor. I don't really know anything about MOSFET transistors, and that doesn't really matter because this is a BJT transistor. And I'll walk you through the basics. So it's made out of three parts. This side is called the emitter side, this side is called the collector side, and this side is called the base side. Basically what's going on here is the transistor kind of acts like a switch, but it uses I think voltage, or sorry, no, it uses current to determine whether the switch is flipped on or off. So over here we have current, although it's moving very, very slowly. You can't see it in the simulation. There's current along this base wire, and it's connected to this transistor. So it's telling the transistor to turn on, and what that does is the voltage supplied from this 12 volts will go through this collector wire and into this emitter wire, where it'll power on the green LED. And this base wire will just tell you to like let this collector current pass through. If this was off, if there was no current in the base wire, the 12 volts from this collector wire would not pass through to the emitter, if that makes sense. And the same thing is happening here, but instead of 12, you have 5 volts, blah, blah, blah. And I'll walk you through kind of how a BJT transistor works. Again, I might make some mistakes, but Okay, so hold on. Let me just show you what it looks like first. Oh, and in a BJT, there's two types of BJT transistors. One's called a PNP, and one is called an NPN transistor. In this circuit we're using an NPN transistor. Though the theory for how it works in a PNP transistor is like the same thing, but it's opposite. So yeah. And this is what I was talking about. You have the base, the collector, the emitter. All right, let me show you okay, well, how do they work? Okay, this is kind of confusing. Let's say this is the base wire. Blah, 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 blah. You have the current going through there. And this is the emitter wire. This is the collector wire. If you know how diodes work, this will be a lot easier to explain. But basically, a BJT transistor is like two diodes connected back to back like this, but it works a bit differently. So normally how diodes work is you have two, it's made of a semiconductor, and I think it was silicon. It might be silicon, the material that they use. And what they do is they dope the silicon with some other elements. So these blocks here, they're silicon blocks, but they've been doped to be N-type and P-type. So in silicon, you have 4 valence electrons, and it creates like a structure with the 4 whatever. And it's, I think, electrically neutral. Could be wrong. Anyways, to what you're doing is you're like inserting elements to create it, to dope it, is what they say. So if you insert elements with more than 4 valence electrons, then you're going to have a surplus of electrons, and that's called N-type doping. And if you insert elements with less than 4 valence electrons, you're creating an electron deficiency, and that's called p-type doping. And these two blocks, so this is a p-typed or a p-doped or p-doped silicon or whatever it's called. I don't know. This is n-type. So there is a lack of electrons here, and there's a surplus of electrons here. I drew them like that. So what you're going to see is the electrons are going to want to flow into these openings where it is electron deficient in the p-type, because n-type has a surplus of electrons. And so how can I explain this? The electrons, when you supply this this base, hold on, I'm gonna need to cut just to like gather my thoughts. Okay, in the circuit or in the photo we showed before, we said that we have a current that flows from the collecting wire, and this base wire is basically just enabling the current to flow through here and into the emitter wire, which is where we had the green and red LEDs. So it would make sense. Oh, and also, this is conventional current, so electron flow will flow the opposite way. So if current flow is there, then electron flow is that way. So it would make sense that electron flows from here to here, right? That makes sense because it's filling the gaps. But like we said, we want a current flow this way, or we want the electrons to flow that way, right? So although this makes sense, this going here does not make sense. So how do we get the electrons from here to go here? So what you're gonna do is this base circuit is gonna create a negative here. And what that's doing is and also this circuit from the collector is gonna create a positive here. And so the electrons from this negative are encouraged to all come into this p-type area. And the electrons in this side are encouraged to, or are attracted to this side. And notice how there are much more electrons in this n-type than holes to fill. Like, what about these 3 electrons, right? The n-type is so much bigger than the p-type. You're going to have spare electrons, and they're not going to know what to do. So once they're here, because there are no more gaps to fill, what they're going to do is they're going to be positively attracted to this positive side of the battery, and it will flow like that. Perfect. And so what you're going to see is, although some electrons are going to go like that, most of the electrons are going to go that way. And remember, conventional current is opposite to the flow of electrons. So really, you're going to see you're going to see a current going that way, which is what we see when we run the simulation. Yeah, see, this is the collector wire. This is the base enabling it to turn on, and you're seeing it flow into the emitter along the arrow. That's how you know. One more thing, and it's these things. I was like, what in the flippity dippity is that? Because in the schematic that my dude Mateo gave me, it's this. We have these things, and I'm like, what are these things? And if you're confused, I was confused too. It's an integrated chip, and And basically you have these logic gates on these little chips, and these little chips need to be powered. And so that's what this is. So VCC, that's like your power coming in, the +5. And the GND is your ground. In this false stat simulation, the logic gates don't need to be on an integrated chip, so this is kind of pointless. But in real life, you'd have that to power the logic gates. And that's what's supplying this current to the base here. Um, and you might be asking, why do we have this capacitor here? Why can't we just have the +5 volts and the ground? So the reason why we have the capacitor is because, like, let's say you have some perturbation with this 5 volts, and let's say it somehow magically drops down to like 3 volts, and maybe that messes up the entire logic gate, or maybe it messes up the entire thing past the logic gate, and you might get like the red flashing light or whatever. You don't want that. You want to have a consistent current going through this logic gate so it operates normally. That's why we have the capacitor. So just in case this 5 volt drops to like 0 or something, uh, okay, I don't know why that wasn't working, but in case this drops, the current from the capacitor will start to discharge and make its way through the logic gate so that it has like a steady current and nothing bad happens. And the same thing's happening here. Um, yeah, and that's basically it. Um, that's what I learned today. If you like this, or if this is confusing, maybe I'll make a better one in the future. Um, I'm a first year, and this is like my first kind of project I'm doing here, and I have no idea, or before like looking into this stuff, I had no idea what's going on. So if you're confused, maybe this will help, but this will probably just confuse you too. I guess this is more of like a record for me to look back on. Um, what else? I think that's it. See you later. Bye bye.